I would like to share with you a particular methodology that we has been developing in the past few decades. We call it the event-based reinforcement learning, and we believe this approach is useful for the general cyber-physical energy systems, including their applications in smart buildings, smart grid, and smart cities. I come from CIFINS, a center in Tsinghua University. So first of all, I would like to share with you three pictures, which is not taken by me, but actually by the public press and a few years ago. So those photos, you can see I have kept the name from the press on those photos just to show I did not do any Photoshop to exaggerate the phenomena. The point is, the global energy crisis has been there for a while. And in the past 1 decade, China, as well as many other developing countries, are also suffering from the air pollution. As a matter of fact, 5 years ago, the 13th five-year plan in China have clarified that we have to save resources, we have to protect the environment, and we have to make sure the development is sustainable. Now, this is not a Chinese issue. Actually, the issue has been global. If we focus on other countries, for example, in the United States, the building operations has been consuming more than 40% of the US energy on annual basis. In China, the number right now is only 19%, but it's rising up sharply. And if we don't do anything right, then that number will catch up to the 40% very soon and might even be bigger than that. On the other hand, there are big energy saving potentials in building operations because we're not talking about new technique such as the insulation techniques as well as other devices. We're not talking about those things. What we're talking about is how we may save energy by better interaction between the buildings and the rest of the grid. Now, first, I would like to share with you some data. If we do not create new ways for the power generation, but we have been using information technology to know better about what to generate, how much to generate, and when to generate, then in that way, we can save about 2.0% of the cost during the generation process. And for buildings, if we can know when and where to provide the HVAC systems, the lighting, so on and so forth, then we can save 3.0%. For industries, if we can better schedule when and what to produce and by how much, then we can save 3.5%. And if we can better connect the supply side with the demand side, then we can save 2.0%. So overall, there is a 10.5 percentage saving potential. And in China, because the majority part of the electricity is generated by coal, so that 10.5% actually equals to about 350 or even 400 million tons of standard coal. So we're not just saving energy, we're not just saving coal, we're actually saving the pollution we emit to the air. So it's a big potential. Now, you might say this problem has been there and those opportunities has been there for a while. Why didn't we take it? Well, because it's hard. Now, there are two types of challenges we're talking about here. One is so-called the ordinary challenges. We call them ordinary not because they're easy, but because they are notorious and they have been studied for quite a long time. For example, the problems we study usually suffer from the curse of dimensionality because when we handle the HVAC control, if you have multiple rooms, then the state space just increases exponentially fast. We call that the curse of dimensionality. The second one is the curse of modeling, because when we handle the collaboration among the multiple buildings in a microgrid, then your decision just becomes so complicated. And even if you can write down a mathematical model for such a system, the parameters sometimes is just so hard to know their actual values. And third, if you take even one step further and try to consider the metropolitan scale of the decision-making process, then what you do right now will actually affect how the system might behave in the next few hours and may even affect the behavior of the system in the next day. So it's a multiple decision that you have to consider in the current stage. Now, those challenges are already very hard, and people, especially the operations research people, the control people, the optimization community, as well as our power community has been spending quite a lot of time to handle those things. But beyond those, we also have those special challenges to address in our cyber physical energy system. One of them is the high uncertainty, because as we can see, the wind power, well, they just fluctuate so large. Sometimes you can see the standard deviation of the wind power generation could be as large as about 10% or even 20% or even 30% of the mean value within 15 minutes. And we have to remember such a big electric power grid involves multiple business owners, and we have different objective functions that have to be achieved in the same system and in the same time. Third, but not the least, is the multi-scale. As we can see from the picture here, from above, we have the photos taken by the satellites. They show how the clouds are moving. But in the middle, we have those uh, velocity measurement provided by the balloons or the other ways. They tell us how large those wings are in different positions. Now, down lower here, we have those wind speed measurement collected from the sensor mounted around the turbine. Those are very accurate, but you cannot do that for all of those wind turbines. So how are we going to merge all of those models? Well, there are so-called multi-timescale and multi-temporal spatial scale models we're talking about. And the question is, how can we utilize all of those models instead of just picking one of them? Well, the short answer, artificial intelligence. But really, what type of artificial intelligence are we talking about? First of all, I would like to clarify what type of artificial intelligence that will be addressed in the rest of this talk. What I'm going to talk about has three foundations in technology. One of them is the Internet of Things. People in nowadays know that we have been making the sensors so teeny tiny and so power efficient, so you can just install them in almost every device we have today. Because of that, we generate a huge amount of data. We call them the big data. In this case, we are not just a human being, but also the sensors we deployed. But on the other hand, the density of the information has become lower and lower, and it will just become harder and harder to get the useful patterns recognized from those huge amount of data. To achieve that purpose, we have to rely on the cloud computing. Well, cloud computing actually has many different names in the past decade. Some people used to call it ubiquitous computing or even, you know, transparent computing, edge computing, but whatever you call it, the point being, computing as a service has become very easy to access and it become almost ubiquitous. As long as you have a cell phone or any other device that can connect you to the internet, then you can utilize the cloud computing service, which is available almost everywhere. Therefore, what's left is the key challenge. That is, how do we make decisions? In order to achieve that, I would like to share with you this very brilliant model called the Markovan decision process. So generally speaking, we have a system state like the temperature in the room, and then you can take an action such as, should I turn it on or turn it off? And because of that action, the system dynamic will just change, like the temperature might fall or temperature might rise. And because of your action, if you turn on the AC, you will pay some electricity bill sooner or later. If you turn it off, you can save your money, but on the other hand, the thermal comfort may not be so good, and people in the meeting room may just feel discomfortable. So after a while, you will have to change your action according to the new system state. Therefore, this decision-making process will just iterate. Now, the question is, how do I make a decision based on what I have so far? Traditionally, your best decision-making should consider all of the information available at hand. But the Markovian property says, if your system satisfies so-called Markovian property, then given the current state, the future becomes independent from the history. Therefore, it is just enough for me to consider how my decision should be available according to the current state. So I can forget about how you arrive at the current state. I should just consider you are right now at the state, and then make a decision according to that piece of information. But even if you focus on that, the problem is still hard. The question is, how can I make these things easier? We call the event-based reinforcement learning is a particular way to address that issue. What is the event here? The event is a set of state transition pairs that may share something in common. For example, in the AEC control problem, which I just shared with you before, then we can define two types of events, the hot events, the cold events. The hot events could be, well, your room temperature just rise be above, let's say 26 Celsius degree. And the cold event is just your room temperature falls below, let's say 16 Celsius degree. Then as long as your system state does not trigger any event, then you don't make any control. But once such a hot event occurs, you will turn on the AC, and once a cold event occurs, you will also turn on your AC. So the events can be used to aggregate the state. And for large systems, your system state could increase exponentially fast. But if you define things right, then the number of events may only increase linearly or even stay as a constant. For example, if I consider a high-rise commercial building, you could have hundreds of thousands of rooms in that building. And in that case, I could define so-called majority cold and majority hot. There are two types of events. In this case, the majority cold means more than 0.5% of the building rooms are filling a cold event right now. Then we define it as the majority cold. On the other hand, the majority hot equals to more than 50% of the rooms in the building are suffering from a hot event. So because of that definition, I use only two events to control the entire AEC decision making for this high-rise building, regardless of the exact number of the rooms. Therefore, event-based decision making on the one hand is making the things easier, but on the other hand, it loses something because event is not state. So technically speaking, it's a partially observable Markov decision process. So we have to use some kind of reinforcement learning to solve this problem approximately. Now, on the left-hand side is the traditional way to solve the problem. We call them the Monte Carlo methods. The Monte Carlo methods will just fix the initial system state and then make a decision and just use simulation to generate the sample path. But because of the randomness in this case, so I have to run the simulation by multiple replications and then use the sample average as an estimation to this action, to the so-called action state value function. Now, what if I look at the system trajectory at a closer and finer resolution? Then I might find out the same state would occur by multiple times. For example, in this case, this red dot, which represents the red state in this sample path, just occurred twice. What if I separate the sample path according to when this red point occurs? Then I could assume those two samples are just like they were generated by independent simulation. I can do the same thing according to the blue states for the yellow states and for the green state. Actually, I can do this for every state that had already occurred in the sample path. In this way, I can generate a lot of estimation for the Q factors, which show the consequence for me to take a particular action after a particular state or a particular event. Then I can compare different actions and figure out which action is the best for a particular event. Now we call the left-hand side the Monte Carlo methods, the right-hand side the temporal difference methods. For Monte Carlo methods, you need a simulation model, and sometimes you need experts to build that model for you. And once your system changes, you have to rebuild the model, recommission the model. It is time-consuming and it is costly. However, on the right-hand side, you don't need a simulation model. What you need is sensors, and sensors are cheap. You can just deploy them to your plants, to your power plants, to your transmission lines, and then you collect data from those sensors. If your system changes, then those sensor readings will change. So hopefully you can use those large number of sensors to govern the dynamic of your complicated system. So left-hand side, you need experts, which is expensive. Right-hand side, you need sensors, which is usually cheap. Now, in the past few years, there is a big rise in deep reinforcement learning. The point is, Even if I collect all of the historical data in my power plant, it is just not enough. The reason is there are many, many other possibilities which has never occurred in your history. So how am I going to make a prediction for those event action pairs? The short answer is you can use a neural network. So if you use your neural network, regardless of it being deep or not, if you use a neural network to approximate the consequence for you to make an action after an event, well, then you can make a prediction. And based on that, you can say much more than what you'd have only seen in your history. So by now, I have shared with you the high-level ideas in the approach. Now, in the following, I will share with you how we apply that idea in three stories. The first one is in smart building control problems. Now, smart building is a terminal in the power grid. Traditionally, we use the thermostat to set a temperature set point and then let the HVAC in the building to satisfy those set point. And you can make it even to be looking nicer and friendly. And we can even do further by allowing the user to complain what they're not happy about. For example, if you feel too hot, too cold, too dry, too humid, or if you just feel I'm not comfortable, even if you don't know specifically how discomforted you are. Based on those feedback, together with the thermostat readings as well as the readings from other sensors, we can generate a statistical learning model for individuals. And based on those thermal comfort models, we can control the terminal devices. And this is a test bed we built in Tsinghua University. And many, many devices in that building can be remotely controlled. So we achieve that optimization through iterative running algorithms. In the terminal level, we control all the terminal devices to make them collaborate with each other so that they can provide a comfortable indoor environment with a cheaper cost. Now, in the remote side, for the devices which we do not see from the room, we will coordinate them so that they can provide enough energy for the terminal device at a lower cost. And those two optimization problems are solved iteratively. Now, we call that idea the I building. We, as the occupants in the room, if we feel something is not comfortable, we will tell the system through the HMI. Then, based on that complaint, the interpreter will transfer that into different set points. And that controller will take over to control those terminal devices as well as the remote devices to satisfy those requirements. Hopefully, that will make the occupants feel much better. Now, if that's not true, then the occupants can always use the HMI to feedback again and close the loop. Now, this is not just an individual problem. Actually, the problem is hard to solve because of the high uncertainty in the demand side and because its lack of quantitative models to capture the coupling among the multiple devices. Well, let's remember we're talking about smart buildings and the occupants are the sole user in those buildings, usually. So if you want to know how the demand is really are, we should know where the occupants are and how many of them, maybe even who they are, what they really want. In order to achieve that, the basic idea is to generate better estimation methodology for the occupant distribution in an indoor environment. In this way, we actually generate a particular methodology to achieve that, which utilize so-called the state-time-based model. And those ideas, taking the statistical model for how long a particular occupant may stay at a particular uh, zone in the building. If, for example, if it is a meeting zone, then probably people are supposed to stay for a longer time. But if it is a corridor, then people are supposed to stay there for a short period of time. So because of those statistical relationship, we can correct the reading from the sensors, even if there are no readings from the sensors. So on the other hand, to make the simulation to be faster, we can build the physical space-based decoupling for fast simulation. The basic idea behind that is to see the similarity among different rooms. Well, although the artist has making our building complicated and more complicated almost every day, but For majority part of the commercial buildings, there is a high similarity among the rooms. Therefore, we would actually simplify and speed up the physical simulation for the energy consumption in high-rise buildings. And that is indeed what we have accomplished. Now, suppose we have solved that problem, then the next step is to connect the smart buildings into a microgrid. And we try to see that if we can let the buildings to coordinate with each other to achieve an even higher energy efficiency. Now, this bottom right is a snapshot of the Tsinghua University campus. So my building, my office is about here, and we have the students would take classes around here. They may just move the library around here, and those are their dormitories. So if I make a circle around the campus, almost 80% of the students as well as the faculties do not leave this circle on daily basis, but they will just shift from one building to the other according to the timetable. So what if I save the money instead of installing a huge amount of storage devices for every building? I could just store a different storage for different building and then connect them with each other. Well, that idea is great. However, it's computationally very heavy. Why? Because you coordinate many buildings together. That will suffer from the curse of dimensionality. And you have to figure out, how do I find a good policy that is also easy to implement? Traditionally, there are two methods. One is so-called, I forget about the complexity of the method. I just utilize optimization to find the optimal. Then that optimal policy somehow may not be easy. Now, the other method says that I could just focus on a particular type of policy. Let's say a threshold type of policy, and then just focus on the parameter optimization for that threshold type of policy. Well, this idea may sound great, but the downside is that your strategy may not be so good. So even if you find the best among the simple strategies, among the simple policies, the performance may not be satisfying. So what should we do? Well, I believe that there is a better way. So what about we can systematically search the simple and good policies? How about we quantify the performance as well as the complexity for every policy? Well, technically it's hard. It's often called incomputable according to the universal Turing machine, which has been shown by A.N. Kolmogorov a long time ago. But although it is incomputable, the complexity is incomputable, but we can approximate it. We can estimate it. So we develop a methodology that can iteratively estimate the quantitative relationship between the complexity and the performance for those event-based strategies. And that idea is very similar to the noise signal ratio. Now here the signal is the difference between the true performance of two policies. And the noise here is my simulation noise. So if your signal is large, that means this policy is very bad. You don't have to consider that as a good candidate. Therefore, you don't have to allocate the future computing budget to that bad candidate. But if the noise is large, that means your estimation is very rough. You have to give me more computing budget so that I can run more simulations to make a better estimation. Well, based on that, we can move to an even bigger scale of the problem. So the city scale. Thinking about the following story. We wake up in the morning in our house, we drive to office, find a spot to charge our car, and then we go to work. Now, the question is, what electricity has been used to charge your car? If that electricity is simply the power which you get from a general state grid, then for example in China, I won't say driving an EV will actually save the CO2 emission. Why not? Because you're not reducing the CO2 emission, you're just changing the position of the CO2 emission. However, if the power that has been used to charge your EV is generated in a renewable way or green way, for example, by the wind power, by the wind turbines installed on the high-rise building, then we say driving an EV actually is making CO2 emission much smaller. But are we talking about the real thing or are we just bluffing here? We have to use numbers. If you consider the city of Beijing, let's focus on this particular case, then we have more than 900 buildings, which is taller than 50 meters, and there are more than 300 buildings, which is taller than 100 meters, even if you consider only those buildings within the fourth ring. And based on the public data, you can forecast the annual power generated from those high-rise buildings by installing those turbines, which is just currently available in the market. The total power would be sufficient to charge more than 50,000 electric vehicles on an annual basis. Well, this claim has a big assumption, which is I have a huge storage. I have a huge battery. I can charge the battery whenever I want. I can discharge from the battery whenever I want. But the question is, if you don't have that a huge battery, can you still make that claim? The short answer is yes, but this is a very challenging question to answer. Why? Look at this problem. Even if you focus on a single stage, then we have the power supply from three different resources. You can get that from the wind, which is almost free, but fluctuate a lot. You can get that from the day-ahead market. It's relatively cheaper, but you have to buy that one day ahead. Or you can get it from the real-time market, which is, very expensive. On the right-hand side, you have the demand, which is the charging demand from the electric vehicle. We're only focusing on the charging load from the EV in this case. Suppose all the other load from the, let's say, the building operation as well as the industry has already been satisfied. So we have to balance the supply with the demand. If this is not hard enough for you, then we just focus on this case. If you consider on a daily basis, then on the right-hand side, you have three different generation curves. The first one is the generation curve from the wind power. They are almost free, but they fluctuate a lot. Then you can have this day-ahead generation curve, which is relatively cheaper, but you have to do that one day ahead. Remember, by then, you don't know much about what's going on one day later. And you do have a prediction, but it is not very accurate. Now, the third choice is a real-time market generation curve. The combination of the three provide me the total generation curve for one day. On the left-hand side, I have the charging demand from one trip of the car, from multiple trips of the car per day, and I have that for every electric vehicle in the city. The aggregation of them provide me the total demand curve. And those demand curve and the generation curve have to match with each other. Well, remember the wind fluctuates quite a lot and the driving behavior of the EV is hardly predictable. Well, there are statistical relationships, but on a daily basis, how accurate can you predict how much miles you are going to drive? Well, thinking about the congestion hours, which is really hard to predict. Then the multi-stage decision will say that because of the battery in your electric vehicle has a finite capacity, so you have to realize that when and how much you charge your car will affect how much miles, how many miles your car can drive. And it is a multi-timescale scheduling problem because, well, one day ahead, the power is cheaper, but the information is not very accurate. One day later, in the real-time market, the power is more expensive, although the information is more accurate. So the basic idea is to divide and conquer. On the upper level, we can aggregate all the demand, we can aggregate all the supply and match them. But in the lower level, you have to distribute the charging load among the electric vehicles. So in the upper level, you decide how many vehicles to charge in total. In the lower level, you decide which one of those cars to charge. Now, in the upper level, we can do those complicated calculations one day ahead using a stochastic model and running a complicated algorithm. But in the real-time market, because the time ticking and the price will just change so fast, therefore we have to make decisions sharply and using a simplified model. So it's a trade-off. It's a trade-off between the forecasting accuracy and the electricity price. In a faster time scale, you have to improve your prediction, and you could sacrifice the performance in the optimization. In a slow time scale, the electricity price is cheaper, but you don't have a very accurate information. So what we have eventually end up with is a stochastic learning model for the day-ahead market. We call that event-based reinforcement learning to solve it. And in the real-time market, we use the model predictive control running on a simplified deterministic, almost a linear model, and solved eventually by Cplex. So we can use this idea and collect that with the rolling horizon to adapt to the real-time new information. But this is not enough. Why? Thinking about the following picture. If you are doing a centralized control, let's say the building owner, the building operator want to collaborate all the charging process in all the EVs for that building. Now, for every single electric vehicle, it is a binary decision. But if you have tens or even hundreds of electric vehicles connecting to the high-rise building, then your total action candidate would just increase exponentially fast. It's actually 2 to the power of n. However, there is a structure in this problem. We can actually show that you can provide a urgency index to rank all of those cars. Those urgency index is a function of two parameters. One is the remaining charging power, and the other one is the remaining parking time. So if you have a lot of power to charge, then I believe the car is more urgent. And if you have a longer remaining parking time, then I believe the car is less urgent. So because of those two things, I can rank all the cars according to their urgency index. So instead of considering the combinations of those cars, I would just consider how many cars to charge. And that is a number from 0, 1, 2, 2, n. So it's only n plus 1 different choices. So it's a reduction from exponential to linear. Now, we try that idea on a numerical example. Eventually, we show that the bi-level, the multi-timescale method, which we propose, can not only just save money, but actually increase the penetration of the renewable power. So this idea can be extended to other cases to include the solar power, the battery, to consider what if I have some knowledge to the generation power of the wind, can I make our method to be smarter? And what if our electric vehicles are driven and shared by a group of customers? And what if I want my method to be decentralized? I want every electric vehicle be controlling its own charging process. Now, this is just a single example for a broader type of problems. We call them the multi-scale policy optimization. The key challenge in this problem is that we have many different models. They are in different resolutions. The high resolution simulation, although they provide accurate performance evaluation, those models are running too slow. The low resolution models, they run very fast, but the estimation is very crude. How can I merge those two types of models? The short answer is, well, you have to define the minimum spatial temporal unit. And based on that unit, we can rebuild the models in the micro level, in the meso level, as well as in the macro level. Then from the upper level to the lower level, we can use a policy projection. And from the lower going to the up, you can use state and action aggregation. Through this projection and aggregation, we can utilize the models in all the levels. So based on that idea, we can actually improve the supply-demand matching. So in a brief sentence, the Internet of Technology has enabled smart buildings, and those buildings may improve the energy efficiency significantly by making smart decisions. Event-based reinforcement learning can address the curse of dimensionality and explore the multi-scale structure of the problem. And that approach has been applied to electric vehicle charging in smart cities and the fast evacuation even in smart buildings. Decision making for IoT is critical for global sustainability, and that is only the beginning. I only have a few minutes left. I would like to share with you a current research opportunity, which is data centers. Data centers, well, because everyone right now is partially or totally suffering from this COVID-19 globally, and many of us rely on data centers to support our online virtual meetings, online classrooms, working environment, online computing. Now, this prediction says that, well, in 10 years, by the end of 2030, the ICT devices globally would consume more than 20% of the energy on an annual basis. And data centers would consume around 3,000 terawatt hour per year. And that is 8% of the energy consumption around the entire world in that year. So data centers are becoming energy monsters. What can we do about this? Well, we can use an index called the power usage effectiveness, PUE, to quantify how efficient your data centers are. Typically, this PUE around the world average is about 1.6 or even more. And the Google data centers has been teamed up with their DeepMind team to reduce that number down to around 1.06 or even lower. On the other hand, many giants in the data center business has made their promise to switch to renewable power. For example, 3 years ago, Google claimed that they have supplied their global data centers 100% by renewable power. And 2 months ago, this year, Google again claimed that they have neutralized all of their historical carbon footprint. But on the other hand, many other giants in China, such as Ali, Tencent, Baidu, and Huawei data centers are still catching up in its green trend. The modularized data center have been well adopted in the mainstream users. Now, the idea is that if we make the data centers to be standardized, then we can simplify the construction, speed up the deployment, and make many processes to be produced in a much lower cost. And this will actually make our simulation, make our forecasting, make our pattern recognition much easier. And by deploying all the sensors in the data center, you can collect their running information and making decisions. And we are not alone. Globally, as Harris has mentioned early at the beginning of my talk, we have actually organized many special sessions and workshops in the leading IEEE societies, like the Control System Society, the Robotics and Automation Society, and even the International Federation of Mathematical Control. And part of my talk today has been summarized and published in these books. So that is the end of my talk. Do you have any questions? Harris?
Yeah, thank you, Samuel, for the exciting presentation. I think was very interesting to see different approaches in cyber physical systems about reinforcement learning. I think everybody can unmute themselves if they want to ask a question or post their question in the chat window. So I see a first question coming, Samuel, from Juan Ospina. One question he has, if he's not mistaken, the reinforcement learning approach that you talked about is based on deep Q learning. If that's correct, how did you deal with discretizing the action space? As he mentioned, temperature or power control may seem as a continuous space sometimes.
Thank you for the question. It's very technical, and to be honest, it's only part of this algorithms, which I have just shared with you. You don't have to discretize your action space. There are quite a few other reinforcement learning algorithms which can deal with continuous action space directly. I do use a particular slide in this QEA to make an example, and in that case, you are using a discretized control actions. But just remember that there are many other algorithms which can handle the continuous action space. For example, the DDPG is one of them. So there are many. It's a very long list.
I see. Okay, thank you. So let me also one question, since until the audience and some other participants ask other questions. Have any of the approaches that you've talked about, for example, the electric vehicle example, besides numerical examples, have been evaluated in other maybe large scale, systems or realistic systems besides numerical simulations?
Yes, I would like to share with you a paper which we just published about 2 months ago.
Hmm.
It is in the control theory technology. It is purely in English, and you can just Google my name and with this keyword a review. So in
Okay.
that paper, we basically summarize all the available data set and those parameters and simulation models for electric vehicles. So what we can find from the internet. And amazingly, there are quite a few because for many researchers in the field, including myself, we suffered for a long time trying to get those real data. And in many of the cases, we don't. So that has been a big difficulty in the past few years. However, the situation has been changing very soon. The reason is many industries are willing to share their data, so with the researchers. Therefore, we just do a literature review and collect those data and put them in a single paper so that you can find that. If you are interested in running some algorithms, testing your own, algorithm to see if you can do better than us, you're very welcome. And there are many, many techniques and there are many real database in a very, I would say, modest scale, hundreds of cars, even thousands of, even tens of thousands of cars, different make and mode. Amazing. So those are just available in the internet. You can just read our paper.
I
And if you don't find that, just remember my email address and send me an email. I will point you to that paper.
think I think there is a time where in the past data was a big issue, so we work only with data either simulated at the lab or um, you know um, not from realistic applications. And now, as we go further, companies and industry are willing to share more and more. So now we have databases booming.
Mm.
So I think as we go through, we'll have more and more data to evaluate algorithms and controls. Any question from the audience? You can unmute yourself again, and or you pose your questions here. Um, so there are two questions actually. Let me ask the first one. Um, uh, Another technical question from Juan Ospina. Can you expand on how do you estimate the signal noise to signal ratio in slide 20 on slide 20? Is this done by comparing the fidelity of your simulation with actual measured values coming from the sensors? This is yeah.
So this is that slide. Oh,
Mhm.
hold on. This this is that slide. I'm not sure. I think some symbols are not showing correctly, but the point is that we are borrowing the idea from a well-known methodology called the optimal computing budget allocation, OCBA. So what we're trying to achieve here is to estimate the relationship between the complexity and the performance among two policies. So if I have a policy, a control policy, I want to assess how complicated is that control policy and how much better performance can that policy be better than my baseline. In order to make that estimation, we have to use simulation, but simulation is costly. So how should I allocate the computing budget among those many different policies so that I can maximize the probability for correctly selecting the best and simplest policy? So that is the optimization problem. That problem has a long study history in simulation and optimization community. Um, for example, there are closed form expressions for small scale toy examples. And for a larger scale problems, you have iterative algorithms try to solve this problem asymptotically. And there have been a lot of methodology with mathematical guarantees so that you can converge to the asymptotic optimal computing budget allocation if you follow certain rules. This signal noise is just one type of those rules. The good thing for this simple signal noise ratio rule is that they are easy to understand and they can be proven mathematically. But, however, there is a but there have been other extensions which can further improve the convergence speed better than this one. So you can have other more complicated, slightly more complicated allocation methodology that can converge to the actual optimal and simplest policy in a faster way. But the allocation would be slightly more complicated. You have to utilize the relationship and even the correlation among those different policies. So I would, the short answer to this relatively long question is that just to Google this name, OCBA, Optimal Computing Budget Allocation. So that has been you can find many, many papers in that domain.
Thank you,
Sure,
Samuel.
you're very welcome.
I see another question from sent to me by Jellum. After he thanks you or she thanks you about the interesting presentation, he's wondering if you may be able to draw a parallel between the two time scale methods with some of the hierarchical reinforcement learning methods that exploring MDPs to apply temporal extensions on them. So that is the question. So essentially, yeah.
Yeah, that's a very, very excellent idea. Well, we haven't tried that though. I believe it's possible. So let me summarize the idea here. We have this idea to utilize the information from different scales. And the way we do that is to build a so-called spatial temporal unit, the minimum spatial temporal unit. And because of that unit, you can technically rebuild all of the other models because they're just, a combination of those the minimum unit. But in the same time, as long as you don't utilize every model in the same time, then you can run those micro, those meso, and the macro models at different computing nodes. So I'm talking about parallel computing. And they don't have to be synchronized. So I'm talking about cloud computing or distributed computing. But remember that those macro models, they run very fast and their prediction are not very accurate. Those micro models, they're very accurate, but they run very slowly. Therefore, it's not just parallel computing, it's actually an allocation of your computing capability or your computing resources across those different levels. So to be accurate, what I'm saying is that you might want to allocate more computing power to the micro level. Because thinking about this, your minute model will have to iterate 60 times before it can provide a reasonable output to the hour model. And your hour model has to iterate 24 times before it can up to provide some interesting output back to the daily model. Suppose we're talking about minute model, hourly model, and daily model. So the number of iterations for different level of models are just different. So when you run this idea on a parallel computer or even on a cloud computing platform, you don't just distribute and allocate your power equally. But on the contrary, you have to allocate that in a smart way so that those models don't have to wait for each other. So that's the relatively long answer to this short suggestion, but I believe the suggestion is a really nice idea. We might want to think about that in the future.
Yeah, that's true. Um, any other question from the audience? If not, I have an additional question. I was thinking about uh, the electric vehicle example that you talked earlier. So assume that I'm driving my car into the parking lot, right? And I anticipate that I'm gonna drive again in a few hours, like in 8 hours after work, right? But something comes up and I need to drive in 1 hour. There is an emergency. I need to pick up my kid from the school, right? So my car's supposed to be recharged, but it's not, right? At the time I have the emergency. So the question is, have you considered the uncertainty level of individuals in your model?
Sure. That's a real requirement from real life. I mean, well, if you give your car and control the charging process by a so-called smart building, then you would like to have some guarantee from the building operator. For example, whenever I want my car, I should have a certain kind of confidence that my car is available. So yes, in our mathematical models, we consider a probabilistic guarantee.
Okay.
But why is only probabilistic? Because you can never be 100% guaranteed. Well, this is a trade-off between the opportunity that you can have a lower charging cost versus the probability that your car may not be 100% ready when you pick up your car. So you cannot get two things in the same time. You either suffer from getting a cheaper charging price, or you suffer from getting 100% ready car whenever you want. Now, the thing how we handle this is to quantify the inconvenience caused by getting a non-ready car when I want it. So it's a penalized term. We have a penalty. We have a penalty to say that if you want to use a car and your car is not ready, then we have to give you some penalty. I mean, we have to give you some compensation as an user.
Yeah.
But of course, in real life, compensation may not be really appropriate in certain scenario. For example, like the scenario you have described, I just have to use the car and my car is not ready. So how much money are you talking about to compensate that if that is the only car available within 10 miles? So, I mean, that is really a good question. And I believe we have to discuss the modeling situation. How do we find a good model to quantify that inconvenience that has been caused to the user?
It also goes one level up, right? So from the control perspective and the design, it's one thing, and then goes up to the policy of this particular implementation and how this would be implemented in real life, right? So as you mentioned, you may want to have a penalty, but in a real situation like this, you may don't want to have, right? So design
Right.
and implementation do different things. Any other question from the audience? If not, actually, we're about on time, and we have time for one question if there is one. Otherwise, let's see. I don't think there is any other question from the audience. I think, Samuel, at this time, we would like to thank you again for your time. It's late night there. Again, thank you for this excellent presentation and the contribution to the task force, and looking forward to check your research output and looking your papers around this area. Thank you again.
Thank you, Harris. Thank you, everyone. I will
Okay.
say good
Bye
night
bye.
and good morning.
Bye bye. Bye bye.
Bye bye.
Thank you, everyone. Bye bye.